Let's talk about Liquid 882 reachable nodes in subdivided graph. So it give us a graph, and it is a two-dimensional array H, and this H for every element that is a H, that is it has three elements, which is the two end of this edge. And also, on this edge, there are some kind of nodes counts. So it gives us max moves, and initially we are setting at node 0. So the n is that there are n original nodes. So it asks in this graph what is the reachable nodes counts. So let's look at the example. We have 0, 1, 10. So this one n equals 3. That means initially there are three nodes. That is 0, 1, 2. And for the age, you see 0 and 1. Between the 0 and 1, there are 10 small nodes. And 0 to 2, there is one node here, and 1 and 2, there are two nodes here. And the things that we have maximum, which is 6. So let's count. So let's look at from 0, we can go this way, right? Go this way, and we can have a maximum to be 1, 2, 3, 4, 5, 6. And we can also go this direction, right? 1, 2, 3, 4, 5, 6, right? So totally, let's count how many nodes we visited. So these nodes, it includes two parts, two type of nodes. One is the original nodes, that is 0, 1, 2. Another is those nodes in the edge, for example, this one, this one, this one, and also all of this, right? So there are two types of nodes. So it add up to 13. So for this question, actually, we are consider consider the things that we should do. What we're thinking about is that, of course, from the edge, we should have a graph to represent possibly at least a map or list of integer array to represent the graph. And the things that the small nodes, it is they are not like the big nodes. They have they have different features. For example, the big nodes, they are related, they are connected by the edge. They are the end of the edge. So that we know from the original nodes, the big nodes one, it means it have some big node charts, right? But for the small nodes, that means that is we are on the edge. It does not have any other path from these small nodes, right? So the small nodes is actually we consider it as some kind of weight or cost, right? And for the bigger nodes, we will say that is a graph H. So, so if we consider this is some kind of cost, right? What we're thinking about is that we can use the Dijkstra way to see if, for example, the cost, total cost we have is smaller than the maximum, right? We should not in queue anymore, right? We have a queue Dijkstra, we're not in queue anymore. So intuitively, we can think about use a Dijkstra way to do this question. But how can we solve how many nodes we visited? Actually, we can have a result outside, right? And we can have a result if there is big nodes we visited, we can add to our result. But the thing is that for the small nodes, how can we do that? Um, so we'll find that the small nodes, it can be visited in some term, like for example 0 to 1, right? It can be coming from the left to right or from 1 to 0. Um, so if we doing during our Dijkstra, when we pull the nodes 0 out, right? We don't know in the other direction whether the small nodes already weighted or not, right? So that is our problem. Um, so how can we think about this question? We should always set these ages, for example, 0 to 1 age, to be processed sometime later, right? For the bigger nodes, of course, we can just use weight. But for the small node, how many we weight, we can we have to do it sometime after we finish this queue process in Dijkstra. So the thing is that when we finish this, um, we can consider from the left to right how many moves we can still process, and also we can process from the right to left how many moves we can still process, right? So the things that how can we handle this? Of course, we can do during the queue while loop, trying to see how many steps we left. Um, but the code is a bit messy, right? So what we think about is we can do something more clear, is that we use a distance array um, to store for each big nodes what's the minimal step, minimal moves we wait to these nodes. So for our Dijkstra, we just doing to for every nodes, we just fill this kind of distance array. For example, to 0 node, the distance is 0, right? And 2, the minimal distance is 2, 1, 2, right? And 1, the minimal distance is 1, 2, 3, 4, 5, right? So what we have for during the Dijkstra, we are going to have a distance array. For example, distance 0 equals 0, distance 1 will be 5, and distance 2 will be 2, right? So if we are doing like this, so we'll see. Um, so we'll see the minimal steps we we choose is 2. The minimal steps with 0 is 0, and the minimal steps with 1 is 5, right? So we can iterate those kind of edges. For example, this edge, right? We know um, the minimal step with node 0 is 0, 0 and 1 is 5, right? And then we have maximum to 6. So that means we can from left to right, we can have 6 moves, right? So we can have 6 small nodes here. And from the right to left, we can have how many moves? That is 6 minus 5, right? The optimal solution is 6 minus 5, so we can have 1 move here. But on this edge, we'll see there are 10 small nodes, right? So that means for the edge, we can count. That is 6 plus 1, that is 7 small nodes, right? So that means that we can add the big nodes counts and small nodes counts separately. So this is a concept. So let's write code for this. And let's first compose the graph. So we are going to have int m equals ages dot length. So what we do is for do we need this m? Actually, we don't need this m, right? We just do for every age on the ages. Going to have for example, we need to have the cost, right? So that cost is how many small nodes for in this age. So U is age is I0 and V equals age is I1 and the cost is age is I2. So what we do is graph U add new int V and so here we should add cost plus 1, right? Because this cost is how many small nodes in this age. But if from 0 to 2, right? We should we'll see we should have the small nodes plus a big nodes, right? So it will be cost plus 1. I think this should and also graph V, we should add new int u cost, right? So why we need to have a cost? Because we need during dark extra we can terminate early. If we are going to pass in for every nodes in our current cost, right? If the current cost already greater than maximum, we should terminate. And we need a distance array equals new int, and right. That means how many moves we are going to wait for the big nodes. So what we do is let's set arrays fill distance integer dot max value, because we want to find the minimum value when we wait this. And also we need know the distance 0 is 0 because initially set sit here, right? Then we're going to have a priority queue, PQ equals new priority queue. So what we're going to sort the comparator will be the cost or moves, right? So we'll see A, B goes to integer compare A1 and B1, right? So we have a PQ offer new int. Initially we are set as node 0, right? And what we do is that while this PQ is not empty, we are going to have int current equals PQ dot pull. And we are going to U equals current 0. And D is our current cost or current moves we have, current 1, right? So, so that means that if we have D is greater than distance U, right? Um, we should continue. Or actually, we can put this one in our next, right? So what we do is that for int eight, this age in so next, right? In this graph, U, let's say v equals next 0, and well cost equals next 1, right? So only when we have the next distance is going to decrease, we are going to enqueue, right? So that means that if d d plus cost, if this is greater equal to distance v, or let's say if d plus cost is greater than the max moves, right? We should continue. Then we are going to have distance v equals d plus update to a smaller one, right? And we are going to PQ offer new int v distance v, right? So after this Dijkstra one, right? We will get for each node what's the minimal moves we can get, right? And for those we cannot move, the distance will be integer maximal. So then we count how many nodes that we can count the big nodes first. So what we do is int result equals 0, right? Then for int I equals 0, I smaller than int I plus plus. And if distance I is smaller equal to max nodes, then we result plus plus. So this is a big nodes one. Then after handle this kind of big nodes, what we do is we handle the small nodes. So for the small nodes, what we do is we iterate the edges. So we're going to have int u equals a 0 and v equals ag1 and cost equals ag, let's say count equals age2. So um so we're going to have int, for example, a equals max dot max 0 max moves minus distance u, right? So if distance is a here this max have two um so get it to be non-negative, right? So only that means only this distance is smaller than max moves. Then we have uh, actual moves or cost from one side to another, from this edge, from, for example, left to right, right? Let's say this is from left to right, and we're going to have int b equals max dot max. This is 0 max moves minus distance v, right? So so this one a and b that means from this edge, each side we can have how many moves. But we'll see the edge, how many small nodes we can have. That is a plus b, but it cannot be greater than the maximum the count of this edge, right? So we're going to have result should add plus to max the mean count and a plus b, right? So in the end, just return result. This should be this is H. So this will be the code. So let's look at uh, the time and space complexity. Here we are iterate H. This will O M, right? So O E or whatever. Um, in this priority queue, right? So actually for every H, we do while loop twice the positive direction and negative direction, right? And assume there are n nodes in the priority queue. So this will be E log n or whatever M log n time complexity, right? And for space, it will be a linear space complexity. Let's also write a Python code for this quick way. So we are going to have graph equals this one or this one in range, and then for u we say in ages we're going to have um graph u equals append uh v and c plus one, right? Because the c is just as a small nodes, and we also need a bigger node as bigger nodes as well. And we need a distance array equals minus by n, and let's have distance 0 equals 0. So we need a PQ equals we are placed with current nodes, bigger nodes, and also current cost or current weights. Um, so what we do is while this PQ is not empty, then we have du equals heap q dot heap top PQ. So this priority queue we put that is sorted by the first one. That will be the the current weight or current cost. We wait for this node, right? U is the node, and we'll see um for UV W in graph U. So we'll see it's new cost, new D equals D plus W, right? So if new D is greater or equal to distance V, or new D is greater than max moles, then we're going to continue. And otherwise, we're going to set distance V equals new D, and if Q dot heap push PQ, we're going to have this tuple that is new D and V, right? And then what we do is that we're going to have a result. Result equals sum for distance for those distances smaller than equal to max moves for I in range, and right, we just find how many distance smaller than maximum, and we iterated the age for U V count in ages. We're going to have A equals max 0, max moves minus distance U, and B equals max 0, max moves minus distance V. And our result should pass equal to mean. We cannot greater than count in A plus B, right? So in the end, just return result.